Okay, we are now doing resistors in parallel. Now we can see that in a parallel setup, the current is not actually equal in all the branches. We see that the current's traveling from here and then it splits up. So some of that goes into R2, I'm going to call it I2. Some of it goes into R3, I'm going to call it R1, I3, and then this is I1. So we can see that current is shared, and how much current will go into each branch depends on the rating of the resistor. As I've talked before, that current is pretty lazy. Charges are pretty lazy. So they want to go through the path of lesser resistance. So smaller the value of resistance, the more current it'll be drawn. Now let's have a look. So I say that total current is equal to I1 plus I2 plus I3? That makes sense according to me. Now, one thing that's constant in a parallel circuit is we can see that ends of all these resistors are actually connected to the battery. So the voltage is equal across each resistor. So I can say that V3 is I3 times R3, which is equal to V. The potential drop here will be I2 R2, and potential drop here will be I1 R1. So I can rearrange that. So V over the total resistance. So we know Ohm's law, V equals IR. So I can rearrange that to I equals V over R. So that's the EMF, and that's the equivalent resistance that we're finding in a parallel circuit. I can rearrange I1 from here, which is equal to V over R1. I2 will be V over R2, and I3 will be V over R3. It's because the total current is equal to I1 plus I2 plus I3. Let's then take V as a common factor and see what we get. 1 over R1, 1 over R2 plus 1 over R3. And if I divide both sides by V, I get the total equivalent resistance in a parallel circuit is actually this. So this is the formula. How do we find the equivalent resistance in a parallel circuit? And this is the working out for it, because current is shared. So the total current is equal to the sum of currents in each branches. We used the Ohm's law and did some calculations, and this is the formula for total equivalent resistance in a parallel circuit. Now let's do an example. So I'm going to copy an example here from your booklet. So let's say we have 40 volt battery here, and we have two resistors, a 12 ohm one and a 24 ohm one. So let's say this is our R1, let's say this is our R2. Let's find the equivalent resistance. So let's say the total resistance is RT. So 1 over RT will be equal to 1 over 12 plus 1 over 24. You should have your green calculator. You can enter this straight away in your calculator and get the answer, or you can do this working out. I'll do the working out once. So 2 over 24, remember we need a common denominator while adding fractions. So the important thing is we did not get RT. We have gotten 1 over RT. So 1 over total resistance is 1 over 8. Now we flip both fractions. So the total equivalent resistance of this circuit is 8 ohms. And it's fascinating to see that the total resistance is actually less than both 12 and 24. It's because not all the charges have to pass through both resistors. So the charges actually split their path. So the total opposition that they're being offered in the circuit is less. Now let's find the total current. So we can use the Ohm's law formula here. So the EMF is 40, total current is I, and equivalent resistance is T. Therefore 40 over 8 equals the total current, which is, the total current is 5 amps. That's it. So it's 5 amps. Now we know that this will also have 40 volts across it. This will also have 40 volts across it because they're in parallel. Voltage is same across each resistor in a parallel setting. Let's find I1 then. So I1 will be V over R1, and I2 will be V over R2. So 40 over 12, and you'll have 40 over 24, whatever. You can use your calculator to find the decimal answer, and that'll be your I1 and I2. So 20 over 6, 6 3 is 18. And so on. You can find R2, I2 as well. So I've done the calculations for finding equivalent resistance in a parallel circuit, finding the total current, finding the individual currents. And that's pretty much it that you need to know for parallel circuits.